So why was it so hard to locate ourselves within the Milky Way? Dust. We just didn't appreciate the dust. So let's take a look again. Here's a visible light picture. The center of our galaxy is right about here. Right about there. And this is Antares, and this is the head of Scorpio, and so this is near the tail of Scorpio. Here's Sagittarius, the teapot, bright stars in the summer sky. And the center of our galaxy is kind of on the border between those two constellations. But there's all this dust here. That's what all the blackness is. And we can't see the center. Now, I, for one, am very glad of that, because I can see how brilliant is the central bulge of most galaxies. In fact, it's said that if we could see the central bulge of our galaxy, it would be about as bright as the full moon. So I don't really want something as bright as the full moon sitting right here, because there are so many neat objects to look at in the summer sky, like Messier 8 here, and these the Omega Nebula, and Eagle Nebula, and there's a whole bunch of great nebulas and star clusters and dark nebulae like the Horse Nebula right here. Looks kind of like Bucephalus from Alexander the Great stories. And I don't want all that permanently obliterated by permanent full moon of light that never ever goes away. I mean, I can put up with a full moon once a month, but permanently that would be a bummer. It did make studying the center of our galaxy a little harder, but we figured out ways, so we'll come to that a little later. How old is our Milky Way? So the globular clusters, again, hold stars more massive than the Sun, have all evolved off the main sequence. So what are these guys doing here? So these are former binary stars, two stars going around each other in a tight binary. And as binary stars, they each had a mass less than the mass that they have now, because now those two stars have actually merged together. They've radiated enough of their energy, mostly through gravitational radiation, that they have merged together, and now they've become a single star. And that single star is more massive than you would expect a star of that mass to still be alive in this cluster. So basically they spent most of their life as low-mass stars, which therefore evolve slowly, and only recently have they become higher-mass single stars. And that's why they're out of place here. But these two are also going to evolve off and become red giants. So there's our galaxy, and there's the central bulge, and there's the dust. So that's what I wanted to show you. The dust plane is thinner than is the stellar disk. The stellar disk is thicker, as we just talked about. So 25,000 to 28,000 light years. I've seen different figures all in that range. Depends on what study. It's a little difficult to try and get it perfect. So, but you know, we got it pretty close. 26,000 light years away. Center of our galaxy. Let's look at just our immediate solar neighborhood. So this is a little hard to see. I got this actually from Sky and Telescope many years ago. But it is a really good way of seeing what we call the local bubble. So we are like the boy in the bubble. We live in a bubble. And the Sun is right down here. A little hard to see, but there it is. And mostly there's not much around us, but if you look in a vertical sense, you can see a little bit of interstellar gas here. Mostly the interstellar gas is piled up in this region here that's many light years away. You know, I don't know, 100 light years away or something. So the local bubble, what is that about? Fairly recently, just 4 years ago, Wallner and then Breitschwert et al., they did some really nice studies of looking at ocean sediments and discovering iron-60, heavy isotope of iron. in the sediments, and iron-60 is only produced in supernovae and has a half-life of only about 2.6 million years. So what was interesting is they found layers. A layer of this iron-60 rich material, 1.5 million years old, and another 2.3 million years old. So it indicates that there was two supernova blasts that happened at these times. And they were relatively close. I mean, compared to 30,000 light years away to the center, these are only 300 light years away. So this is only one, both of these supernovae were only 1/100th of the distance to the center of the galaxy. And they agree pretty well from the kind of blast wave you'd expect from that with the local bubble size and expansion. So we think that's probably what happened. This is just a beautiful photo. I've tried to reproduce a photo like this with my own equipment, but I've so far failed. The sensitivity required is very high. These colors look gorgeous here, but you need really, really pitch black skies to try and get down to sky brightnesses that will allow you to see this. So this bright star here is Antares. This is a red supergiant. This star here is Delta Scorpii, or rather, I think this is actually, yeah, this is Delta Scorpii, and it is very hot. This star is very cool, is only about 3,000 degrees, 2,500 degrees. This star is very hot, maybe 30,000 degrees, and it's ionizing the hydrogen around it to give you this nice, sharp fire engine red color. The orange color you see here is really just light reflecting off of dust. It's the red light of Antares reflecting off of rather large dust grains. There's also dust surrounding Rho Ophiuchus, which is this star here, smaller dust which will scatter blue light. And also Rho Ophiuchi is a much hotter star. It doesn't give off much red light. So mostly you see blue light. And there's another example of that up here. And then there's M4, that's a globular star cluster. And here's another globular cluster. So close to one of the brightest stars in the sky. The head event of Scorpio is actually a pretty neat place to explore in summer skies. So there's the local bubble. And there's the sun. So the local bubble kind of encloses all this. And we are on the inside edge of the Orion spiral arm, or what's sometimes called the Orion spur. It's a short segment of spiral arm. The next spiral arm, closer to the center of the galaxy than us, is the Sagittarius spiral arm. And that's right here. And there's some associations there. The Scorpio-Centaurus Association, that's an old star cluster, open cluster. And here's another map showing our galaxy. Putting together a map like this is actually very, very difficult because we can't see our galaxy from the vantage point that we show in this image. The sun is right there on the inside edge of the Orion arm, or what they call the local arm here. The next nearest spiral arm to the center is the Sagittarius arm. Then there's the Scutum Crux arm. And then there's the 3 kiloparsec arm, and then there's the center in here. And one thing really interesting that we didn't know until the 1990s, which I still think of as pretty recent, is that we don't live in an ordinary spiral galaxy like the Andromeda Galaxy. We live in a barred spiral. And the bar is obvious in this drawing here. It's a short stubby bar. It doesn't extend out anywhere near as far as the sun. And so it actually took pretty good mapping of distances and velocities for certain red giant stars in order to be able to map out this short piece of straight spiral arm, which we call a bar. So we live in a barred spiral. We'll talk about galaxy types in the next chapter. But we've already introduced spiral arms. What are spiral arms? That's the next question. Spiral arms are places They are spiral density waves which sweep through the gas and the dust. They compress it, and being higher density aids star formation, and the star formation makes new stars. Some of those new stars are massive. The massive stars are very, very brilliant, and so those are what show off the spiral arm. Now, by the time the spiral density wave is moved over to here, those massive stars, we remember from our last chapter, they only last a few million years. And one thing I didn't mention, but I will emphasize now, the sun takes 250 million years to go around the galaxy once. So stars that live only a few million years, they don't even get to be 1 year old. They die in infancy. And by the time the spiral density wave, is moved on to here, then these stars here have already died. They've already blown up and become supernovae, and they're gone. And now the stars you see are here. And basically it's because the lifetime of stars that are massive enough to really dominate the light of a spiral arm, the fact that the lifetime of those stars is very short compared to one orbital period around our galaxy, that's why spiral arms are so clearly evident. It's because they're narrow, and they're narrow because the amount of time that those stars are alive and therefore show off is short. Okay, so this now is a drawing. This is not a real photo of any kind, but it's trying to show the distribution of a stream. So our galaxy is a big, massive galaxy. We live around a pretty average, ordinary star, but we don't live in an ordinary galaxy. We live in a rather extraordinarily large galaxy. We live in a pretty beefy, big galaxy. And what you're seeing here is a small galaxy that has fallen in. And as it falls in and orbits around, it's getting pulled apart. So it's getting stretched into a noodle. So remember the tidal force. Things that are gravitating towards other things, the near side is pulled more than the far side. So there's this secondary effect of being stretched while you fall in. And if you're as loosely bound as small galaxies are, then it's pretty easy to actually pull them totally apart, almost like the way you make cotton candy in a carnival. Now this is an actual set of photos, and then rendered with, with colors and so forth to make a map. But these are actually photos that have been reassembled. And the most obvious thing here is the galactic plane. This is the plane of our galaxy. This is an all-sky image. So this place here is the same as this place over here. And what I wanted you to notice is the Magellanic stream. There's the large Magellanic Cloud. That's a galaxy. There's the small Magellanic Cloud. It's a piece of the same galaxy. Here is more stars in blue. And there's little bits and pieces of stars, clusters and things, and globular clusters that you can see along this whole stream. So this is now called the Magellanic stream. And clearly it is a single larger galaxy that got pulled apart as it fell in too close to the Milky Way. And the star systems are still visible, but at some point they'll probably fall in far enough to just merge with the stars in our own galaxy. This is low-metallicity gas from far away falling into the Milky Way. So you see streams in several places here, and these streams are tidally distorted intergalactic gas and dust, and even in some cases stars, like here and here. So that's what happens is low mass galaxies tend to aggregate and be formed in the neighborhood of big massive galaxies, and so we've got our whole little fan club of little teeny galaxies that follow us around. Okay, so now let's take a trip to the center of our galaxy and see what we see. So in visible light, mostly you see dust. You can't really see the center of our galaxy. Again, it's right in here. Now, if you look along this area, though, you can see a little bit of the central bulge of our galaxy. In this area, I think it's this area, that's called Bada's window, a place where you can see down close but not at the center of our galaxy without too much dust obscuring your view. Now, this is an infrared picture, and an infrared picture is going to show stars and the plane of our galaxy, and now you see the dust as well. That's the darkish stuff, but it's nowhere near as obvious as it was in visible light. This is part of the 2-mass survey. 2 micron is what that stands for. 2 microns is about 4 times the wavelength of the visible light, and that's rather long, and you're really going to be dominated by infrared light now from a cooler stellar population, and you're going to be able to see through dust much better. So there's the large Magellanic Cloud, and there's the small Magellanic Cloud, and you don't really see the stream that goes with it because that's something you would more see with radio telescopes. The hydrogen gas gives off radiation that you can see. Another image, another infrared image, and now the large Magellanic Cloud and the small Magellanic Cloud are more obvious. The light that you're seeing here is red light, and there's a globular cluster right next to the small Magellanic Cloud, and in fact most of these little teeny globby things that you can see in the photo here, these are globular star clusters. They are dominated by red giants. Red giants are cool enough that they give off a fair amount of infrared light, and they're pretty concentrated, so they're kind of obvious. Okay, and now we're combining 2-mass data and also the MSX, which is a mission that looked at even longer wavelengths. And now you can see something's going on down there in the center of our galaxy. It's not, you don't really see the dust so much anymore. You're able to look through it. So let's do that again. The galactic center's right there. And now we zoom in. And this is an image taken in longer wavelengths, long enough to show these rings here are made by stellar explosions, we think. Supernovae that have gone off. So there's active star formation going on not too far from the center of our galaxy. And then if you look in towards the very, very center here, we're going to take that and blow it up a little more. And it looks like this. And it looks like this. And when you see that, you should probably get a bit of a flashback and say, oh, that kind of looks like those prominences around the sun. And yeah, they're actually closely related. It's the same physical thing going on that dominates the light here. What this is radio, well, in this case it's radio light, but it's dominated by, well, let's say the structure's shape is dominated by the magnetic field, just like on the sun. So magnetic fields near the sun channel the gas near the sun and constrains them to follow along the field lines. And the same thing must be going on here. So anybody who's looked at enough magnetic field dominated photos could look at this and just say, oh, this is too obvious. These are magnetic fields that are channeling this stuff to only follow along the field lines. Huh. Why would that be? And why would there be radio radiation coming along these magnetic field lines? And then you realize that, well, if you have high-speed electrons, those electrons would be spiraling around the field lines, and that's a form of accelerated motion that would give off light. In this case, very long wavelength radio light. Well, why is there free electrons here? I mean, don't electrons like to find protons and be together and be neutral hydrogen? Yeah, usually. So that's a giveaway that something is powering this down here enough to send out enough ionizing radiation, not seen in radio here, that is actually ionizing this gas. So it's knocking the electrons and the protons of normal hydrogen and knocking them apart.